Hi, my name is Daniel Lissis, and I'm presenting our work, Know What You Don't Know, Consistency in Sliding Window Filtering with Unobservable States, applied to Visual-Inertial SLAM. Now, why do we care about estimating unobservable states? As it turns out, several real-world estimation problems have states that are unobservable. These include legged robots, projectile trajectories, and simultaneous localization and mapping, or SLAM, problems. When real-time estimation is needed, two types of approaches are typically considered. Filtering-based approaches, such as the extended Kalman filter, which estimate one state at a time, and optimization-based approaches, such as the sliding window filter, which estimate a number of states together. The problem is that these estimation approaches become inconsistent when faced with unobservable states. This means that, as shown in the example plot, the uncertainty on the state no longer captures the true state, meaning that the error becomes greater than the uncertainty. This occurs because traditional estimation approaches falsely gain information about unobservable states, and as a result become overconfident. This is problematic because inconsistent estimates cannot be trusted. Although solutions to this problem exist, they are largely focused on filtering-based estimators and are presented as being application-specific, without a clear way to implement them in new problems. This paper thus focuses on the inconsistency problem in the less studied optimization-based class of estimators. In particular, we present two application-agnostic requirements for ensuring that consistency is maintained in sliding window filters involving unobservable states. We then apply these two requirements to the problem of visual-inertial SLAM using IMU pre-integration, an algorithm formulation that has not been previously studied from the perspective of consistency. To present the two requirements, let's quickly review the process of implementing the sliding window filter, at the core of which is maximizing the posterior probability density function. Specifically, we wish to find the state x that maximizes the probability that the state corresponds to the provided prior and measurements. This problem is equivalent to solving a least squares problem of the following form. Finally, to solve this in practice, we linearize the least squares formulation and then use Gauss-Newton or Levenberg marker to get the final answer. Now, for problems with unobservable states, the Jacobian of the linearized problem has a null space that corresponds to the unobservable directions. It is critical for the algorithm to maintain this null space in order to prevent information gain. Leaving the specific derivation to the paper, the two requirements that we arrive at stem from this null space. The first requirement states that even prior to algorithm runtime, the Jacobian of the linearized algorithm must have a null space. Once requirement one is satisfied, the second requirement deals with the algorithm during runtime and states that the Jacobian must maintain the same null space even when evaluated at different linearization points. We apply these two requirements to the problem of visual-inertial SLAM. The VI-SLAM algorithm uses cameras and IMUs in order to estimate a map of the environment and to localize a robot within that map. Modern VI-SLAM algorithms make use of sliding window filter and IMU pre-integration. The VI-SLAM algorithm has four unobservable directions: rotation about the gravity vector and absolute translation in the world frame. As shown in the figure, these mean that the entire SLAM solution can be rotated about the gravity vector and translated in the world frame without a change in the relative results. Traditional VI-SLAM formulations see the information gain problem appear in all four unobservable directions. So, how does a modern VI-SLAM algorithm deal with unobservable states? We first use a simulated environment to remove all real-world inconsistencies to study this question. Using our two requirements, we show that using IMU pre-integration in orange is actually needed in order to maintain consistency in certain VI-SLAM setups where direct IMU integration in blue fails. In these experiments, the NIS, a measure of consistency, should be approximately 1 for a consistent estimate. Note that we compare many other VI-SLAM combinations in the paper and show that meeting the requirements leads to consistent estimates. We additionally include real-world results run on the EuroC machine hall sequences. In these results, we note that things such as imperfect intrinsics and extrinsics, errors in data association, and unknown noise parameters result in inconsistencies regardless of the two requirements. However, we showed that setups that meet our two requirements tend to be more consistent than those that don't, with consistently lower NIS values. In conclusion, our paper presents two application-agnostic requirements for ensuring sliding window filters with unobservable states remain consistent. We show the value of these requirements within the context of designing visual-inertial SLAM algorithms.